Welcome back, AP Stat. This is the last installment, the fifth and last installment of Chapter 19, the first chapter on hypothesis tests, specifically for the proportion P. Let's answer a couple of questions that will employ some knowledge from the last couple of videos. So we have a bank. A bank is testing a new method for getting delinquent customers to pay their past due credit card bills. The standard way was to send a letter costing about 40 cents, asking a customer to pay. That worked 30% of the time. They want to test a new method that involves sending a DVD to customers, encouraging them to contact the bank and set up a payment plan. Developing and sending the video costs about $10, which is a lot more than 40 cents a person, and that is going to be important later. Per customer, what is the parameter of interest? What are the null and alternative hypotheses? All right, so let's first consider what is the parameter of interest and what are the null and alternative hypotheses. Feel free to pause the video, try this one on your own, and unpause when you are ready to see an answer. All right, I'll assume we're ready to continue. Here is the answer. P is the proportion of contacts, which whatever method you would like, whether it is the letter or the DVD, resulting in a payment of past due bills. All right. The null hypothesis is that the proportion of contacts resulting in payment of past due bills is 30%. While the alternative hypothesis, I'm going to say, is P is greater than 0.3. Now, you can make an argument that its P is not equal to 0.3. However, later in the problem, it would be helpful for that to be the alternative hypothesis. So here comes the next problem. The bank sets up an experiment to test the effectiveness of the DVD. They mail it out to several randomly selected delinquent customers and keep track of how many actually do contact the bank to arrange payments. The bank's statistician calculates a p-value of 0.003. What does this p-value suggest about the DVD? Think about how you would interpret that p-value, specifically considering our alternative hypothesis. Let's look at the answer. A p-value of 0.003 indicates that we should reject the null hypothesis. There is significant evidence that the DVD improves the proportion of contacts resulting in payment of past due bills. So since our alternative hypothesis is P is greater than 0.3, a low p-value would say we should not only reject the null hypothesis, but support this claim here that the proportion is greater than 0.3. Now let's look at our last problem. The statistician tells the bank's management the results are clear and that they should switch to the DVD method. How about you, statisticians? Do you agree? What else might you want to know? Think specifically about the term effect size from the last section. If you need to rewatch the video or reference your notes, now would be a good time to do so, but think about how effect size would relate to this problem. Okay, I'll assume we're ready to continue. If you need more time, pause the video. If not, here comes the answer. I am not sure the bank should make the switch. I would like to have a confidence interval for P to get an idea of the effect size of switching methods of contact, especially considering the cost difference between the methods. We're talking a difference of 40 cents per customer versus $10 per customer. That's a significantly more expensive option. So I'd want to get the idea of the effect size. What is effect size? It is the distance between, so it's a positive number, distance between the true proportion and the assumed population proportion. So the assumed population proportion at the start of the problem was 0.3. Now this alternative hypothesis, which we sided with after doing number 5, is very, very likely true. All right, with a p-value of 0.003, it is almost guaranteed true. So that means the proportion is significantly greater than 0.3, but what does significantly greater look like? I would really like a confidence interval for P to get an idea of where the true proportion lies. If we're pushing like 50, 60%, that's a big effect size, and I think we should go through with the change. However, if we're going from, say, 30% to, I don't know, 35%, I don't think that justifies changing the cost per person from 40 cents to $10. So I really want to see a confidence interval to get an idea of the effect size, all right? How much is that proportion going to change? All right, now let's do one more big old problem involving baseball. Anyone who plays or watches sports has heard of the home field advantage. Tournaments in many sports are designed to try to neutralize the advantage of the home team or player. Most people believe that teams tend to win more often when they play at home. But do they? If there were no home field advantage, the home teams would win about half of all games played. To test this, we'll use the games in the Major League Baseball 2017 season. That year, there were 2,430 regular season games. It turns out that the home team won 1,312 of the 2,430 games, or just shy of 54% of the time. Could this deviation from 50% be explained just from natural sampling variability? That's the null hypothesis. Or is it evidence to suggest that there really is a home field advantage, at least in professional baseball? That would be the alternative hypothesis. Oh, by the way, this is a picture of a Citizens Bank Park. I am low-key a Phillies fan. You probably call it on, if you're not one of my students, that I am a hardcore Philadelphia Eagles fan. And if you are one of my students and you didn't know that, you have probably been asleep the entire class. Okay, so the null hypothesis is P equals 0.5. The alternative hypothesis is P is not equal to 0.5, where P is the proportion of games the home team wins. Let's look at our assumptions. We can assume the outcome of one game will not affect the outcome of another game. How can we confirm independence, though? Well, we need to look at a couple of conditions here. The 10% condition. We are interested in home field advantage of Major League Baseball for all seasons. While it's not a random sample, so you can't necessarily assume randomization. We're only taking games from one season. These 2,430 games are way fewer than 10% of all games played over the years. That is an understatement. Okay? So we cannot assume randomization. Okay, because we have chosen games from a specific season that may have had different circumstances than other seasons. So we need to take our results with a grain of salt, even if there is a really clear result in terms of our p-value. So success fail condition. We need to check out n times p naught and n times q naught to see if we can expect at least 10 successes and 10 fails. If we have n p naught, that would be a sample size of 2430 times 50%. That's the number in our hypotheses is p naught or p sub 0. And that would be 1,215. Same deal with n times q naught. That would be 1,215. That is, of course, greater than 10. There you go. And again, with randomization, these games are not randomly selected. All right. We can assume that the regular season games of 2017 are similar to those in the recent past and the near future. However, again, we need to make sure we do not apply our result too broadly. So we'll use a normal model to perform a one proportion Z test. So here I am in the calculator. I am in one proportion Z test. I have my P sub naught equals 0.5, X equals 1,312, which is approximately 0.5399 times 2430. So we would round up to 1,312, and that is how many wins we would have for the home team. And that agrees with the problem. Great. We have 2,430 is our sample size, and the P is not equal to P sub 0. That would be our alternative hypothesis. P is not equal to 50%. And we hit calculate. And we get a p-value which looks like a big number until we see this E-5. Now, you probably have seen this up to this point in the year, but just in case you're not sure what that means you bump the decimal 5 places to the left. That's a really, really small p-value. So how do we interpret this result? A p-value of about 0.0001, if you were to round to the nearest 10th, 100,000th, 10,000th, if you were to round to the nearest 10,000th, it would be 0.0001, says that if the true proportion of home team wins were in fact 50%, an observed value of a little shy of 54% or more extreme would occur less than 1 time in 1,000. So a proportion as extreme as ours or more extreme would occur less than 1 time in 1,000. That's not very likely. With a p-value that small, I reject the null hypothesis. I have reasonable evidence that the true proportion of home team wins is not 50%. Thanks to the textbook for that very precise description in the context of the problem. Now, what do we do with that information? We're going to now find a confidence interval at 95% confidence. Let's go to the calculator to do that so we can get an idea of the effect size. Here we are again in 1 prop z int this time. We have x is equal to 1312, n is equal to 2430. So that's our number of successes for the home team as opposed to our sample size. And we want a confidence interval that is 95% in terms of its confidence level. So we're going to go down to calculate. And here we go. There you go. So there is your confidence interval. This confidence interval on the left side specifically is above 50%. So just by this confidence interval, we can say there is a significant difference between where we would expect the proportion of home team wins to be as opposed to opposed to 50% and even 50-50 split. All right. So this gives us an idea of the effect size. All right. How far off the true value of the proportion of wins for the home team is from 50%. Anywhere from about 2% up to almost 6%. That is a big difference potentially. Now, just to make sure that this result is applicable, I'm going to go through the motions a bit and check the conditions. We need to observe at least 10 successes and 10 fails, not just expect them in order to do a confidence interval. There were 1,312 home team wins and consequently 1,118 losses. Both are at least 10. We have observed at least 10 successes and 10 fails. Therefore, we can form a 1 proportion z interval. We've already checked all the other conditions for 1 proportion z interval before. We just needed to make sure that we have observed, not just been able to expect, at least 10 successes and 10 fails. All right, so just as the calculator told us, our interval is about 52% to 56%. Here is the answer expressed in terms of a plus minus. This is a common way of displaying confidence intervals. This is what we get from the calculator explicitly. And this is your homework. Hope you enjoy it. Hope this lesson was helpful. And I hope you enjoy this interesting, fun little interaction between me and one of my former students, Lincoln Waltenbaugh. Your legacy lives on.